Oh boy, Ben, I think we're recording.
There we go. Okay, wow, okay. I'm not
We're
ready. I'm
going.
not ready.
We're going. The nice thing is that we both know, Ben, that it is currently June 14th, 2024.
Right.
And so for once, we're actually like exactly on time recording an episode.
We just did a great big live stream, to my memory.
Yep, we did a great big live stream where we fully caught up, and then now we just have to do this one thing.
Yeah.
This might come back. This I'm gonna call it untruth is gonna come back to bite us in like half an hour when we immediately start talking about 180. But the audience won't know.
Listen, even if by chance we happened to fall behind, we can just say that we were lazily initializing the podcast.
Oh, I like
which
that.
Which might be a thing to call back to later, right?
The other thing that's really nice about the 6 weeks cadence of Rust releases is that you catch up really fast. Right? Like if you do 2 releases, suddenly you've jumped 3 months. That's great. Okay, I think we should dive into 179, Ben. And the first thing here is inline const expressions. Now, I think my initial question is, what are const expressions?
Right. So generally, it's pretty easy to understand, right? So a const is normally something that you declare anywhere, really. Normally, you declare it at the quote unquote item level, which is where you normally declare your functions. But const can actually go anywhere, just like a lent or anything, right? Anywhere you can expect a normal declaration. And they evaluate or they create a named variable, quote unquote. It's a constant. It's hard to call it a variable, right? It's an item where effectively the right-hand side of the equal sign gets copied and pasted anywhere that you use the name, right? And so const uppercase foo, because they're always screaming, right? If the right-hand side is 42, then the compiler will effectively copy-paste the value 42 anywhere that you refer to foo. Or if you had a more complex expression, right, it'll effectively do the same, which can cause some kind of confusion if you have something like, on the right-hand side that's a constructor of some kind, and you thought it might be, mutable or updatable, but in fact it is effectively just copy-pasting the implementation everywhere you use it. It's basically a way of doing named constants. And so it's been somewhat repurposed, the keyword, right, to also be like, hey, if we want to evaluate things arbitrarily at compile time, let's just use this const block, and now anything that happens inside of this const and then open close brackets, and it happens inside those brackets, is guaranteed to be evaluated at compile time and kind of compiled down to something that can be conceptually copy pasted anywhere as a single value of some kind. Right. And so you can do let foo equals const block something, or you can also, as the blog post mentions, you can use these in other expressions. And so it's like let foo equals and then an array, right? Square brackets, const none, and then repeat that 100 times, right? So you can use these pretty much anywhere that an expression is expected, I'm pretty sure.
I think what sort of landed here is specifically the ability to use it anywhere where you can use an expression, which I don't think was previously true, or at least there were some restrictions on where you could use it. And one of the things they call out in particular here is that you can now use these inline const expressions also when in generic contexts. Well, what's the implication here? Like, where could you not use it before?
Right. So we had a long talk about this before the podcast, where the idea of const, imagine you're in C. You're a classic language like C, a venerable language like C, and you declare something outside of a function, right? Int, foo, whatever, right? Normally, you're doing that because you want to be able to access that everywhere. And so in Rust, this kind of became static items. The idea of, we have something and it lives somewhere in the ether. It lives effectively outside of every function, and it then has its name importable to every function below it, right? So you can refer to this global variable. It is a globally scoped thing by declaring it outside of the function. And Rust inherited this, and kind of like many things, there may have been better designs if you are willing to judge this in the past. It is certainly convenient to be able to use a globally declared variable in this way from any interior scope, but it means that the notion of things of scopes in general kind of becomes murky if you expect this const item to be able to refer to things that only exist in certain scopes, like generic parameters. So that just isn't allowed. But because things that are lexically scoped, like let expressions, do exist within given scopes, you can instead of doing const empty trying to capture some generic parameter, you can do let foo whatever, right? And then use that there. Use a const block on the right hand side, and it should just work out.
I see. So the thinking here, I think you gave a good example before we started the podcast. Although we obviously don't exist outside of when you listen to us, so there is no before or after. There is only during. So we're making this up as we go. Which is, imagine that you have a function foo and it's generic over some t. Inside of foo, you declare another function, a function bar, and then after foo, so not inside foo, but after foo, you declare a const baz. Then inside of the body of the function foo, so the nested function definition, you're allowed to refer to bar, even though it was defined after and outside of foo. Like foo was never given access to the constant. Sorry, the bar was never given access to the constant baz, but it just kind of lives in the global scope for some reason. But that doesn't really make sense for let bindings, which are lexically scoped. Like they only live from where you declare them and onwards, and only in that scope. They don't magically become available elsewhere. But then, as you pointed out, Ben, like the interesting thing here is what happens with if the outer function here is generic over some t, because the nested function bar, it doesn't, like, it is not generic. And in Rust, at least the way things currently stand, if you declare one function inside of another, that inner function is not a closure. It is a freestanding function that doesn't capture anything from its environment, which also means it's not allowed to capture any of the generic parameters of the scope. It just so happens to be declared. And const items are the same way. They don't get to capture anything because they have this like weird global property. But once you put these const expressions in expression context is something like a let, then that changes, because the let does live in a particular instantiation of the generic parameter of the function that they're in. They don't exist in this weird global context. And the implication of this is that when you're using these inline const expressions, like using it in a let, you are allowed to refer to generic parameters that happen to be available at the time. So if you had a function foo generic over t, inside of it you can say, let bar equals and then a const block and say, for example, none : t, to indicate that you actually want that generic value to be of the generic type option t. And this is a little interesting if you start digging into the implementation, right? Because what that means is the compiler ends up generating a different const for every possible t that function might be called with. Because it has to, right? A none of string is different from, it's a different type from, a different like bit pattern almost from a none of, vector, right? Like these are two different types, but because you're trying to create a const of them, and they have t in them, the compiler effectively has to construct two consts, one that is for the case where you're using the const expression and the function parameter is generic over string, and one where the generic type parameter is a vec. And so there's like machinery that had to land in the compiler here to make multiple instantiations of const to work in this generic context. The next thing that's up in 179 is bounds in associated type positions. So the thinking here is that you can say, if you let's say you want to be generic over something, some I or some t, and you want to say where t implements iterator, but you also want to say that the item type of the iterator is, for example, copy. Then previously you had to say, generic over t, where t : iterator, comma, t : item, or t, if you wanted to use the explicit syntax, t as iterator, : item, : copy. And with this new change, whenever you have bounds like this, you can just write t : iterator, open angle bracket, item : copy. So you can declare the bound in the same place where you declare you can declare the bound on the associated type in the same place or inline with where you declare the overall bound on the type parameter. And the blog post here lists a bunch of different ways and like places where this can be used. Were there any that jumped out to you here as being particularly interesting, Ben?
Right. I think that, so I think we should in general try to call out for any given feature. If we think that there's places people should go through their code base and like try to use these features to simplify, that's a good thing, right? And so I think the where clauses one mostly speaks to me, where previously, if you were like using where clauses to try to constrain associated types for your traits, you can now make that much more compact. Instead of having two lines where one of the lines has to use a super verbose sort of like, associated type from trait syntax, you can just have a single where clause and it looks totally natural, looks totally normal. It looks like a thing, one of those features that should have always existed, right? Ideally, it doesn't actually like add new surface area. It just makes things more consistent and more natural. Like you would have, if you would expect to be able to do this, and now you can. And so if you happen to have a bunch of associated types being within where clauses, I think now you can simplify a lot of your code there.
Yeah, I think that the other one that's sort of struck me as being not just like nice, but actually it makes an ergonomic difference is that or adds a feature, if you will, almost is this this point that you can now use this in super traits. So the example they give in the release blog post is, imagine you declare a trait copy iterator and you declare it to be a super trait of iterator. So you write trait copy iterator : iterator. Then now you can say in that sort of colon iterator, you can say open angle bracket item : copy. And what that means is that the copy iterator trait is a super trait of iterator where the item type is always copy. Now, previously, you could write this as trait copy iterator : iterator where self : item : copy. But that doesn't mean quite the same thing, or at least it doesn't have the same implication for uses of that trait. So with the old definition, like where you use where self : item : copy, anyone who uses your copy iterator trait, like let's say they take an impl copy iterator somewhere, the associated item type will not be inferred by the compiler to be copy, because it's not a definition of the super trait. It's just an additional where bound on the trait. And those are treated separately from like the super trait implication almost. And so you would actually need to write, function foo takes a t : copy iterator where copy iterator : item : copy, even though that feels like it was sort of implied by the where clause on the copy iterator trait definition itself. But with this new syntax, if you write trait copy iterator : iterator angle bracket item : copy, so it's like the bound on the associated type is like inlined in the super trait declaration, then the compiler will actually understand that this is implied wherever the trait is used. So in callers that, like, let's say the function foo generic over t : copy iterator will now automatically, the compiler will infer that its items must be copy. And so that feels like a pretty meaningful ergonomic thing for anything that uses super traits, or the people who use things that are super traits. You'd like avoid a bunch of these like propagation of where bounds that feel like they were really implied. Did you have any others you wanted to touch on here on this like new bound syntax?
Not particularly. I mean, it just as we were both kind of like amused at, some of these release notes trying to describe new features, sort of sometimes lapse into jargon if there's no better way of describing what the new power is. And we were both laughing at the one of the bullet points here is this allows constraining the nested rigid projections that are associated with the trait associated types. And neither of us have any idea what nested rigid projections are. And I don't know about me, but I know that if Jon doesn't know what a thing is, I assume I will never need to use it. If it's that obscure, I assume that's never going to be relevant to me.
Yeah, it's one of those fun things where, like, I think I could probably guess what it means based on the example code they gave, but like I have never heard that description of a thing before.
Mm-hmm.
Like, I kind of could say what a projection is, but I don't know what a rigid projection is. That just seems different.
Mm-hmm.
Okay, let's then move on to the next one, which is extending automatic temporary lifetime extensions. So that's extending twice in the same headline. What's this about, Ben? And what are temporary lifetime extensions?
It's a big topic, really. I think, honestly, it'd be a great topic for one of your streams. I think a deep dive into lifetime extension and temporaries in general. I think it's kind of an under-documented aspect of Rust, where you can imagine, right, so a temporary is if you use some kind of value inside of an expression, how long does that value live for? Which matters for the case of lifetimes in Rust. You really need to care about when a thing goes away. And so in languages like C and C++, this is often a source of errors, right? Where you might create a value inside of an expression that's rather complex, and then because you don't understand how long temporary lives for, it might go away and become uninitialized when you actually want to use it, or some reference to it escapes somewhere, which can cause use after just a dangling pointer, right?
Okay, so just to understand, so an example of this would be something like I call a function foo, and where I call the function foo, the argument to foo is like vec : from iterator, and then I give some array in there. So like the vector is created in order to produce the argument for foo, but like how long does that vector live for?
Mm-hmm.
So the vector would be a temporary, right?
Right. And again, in an attempt to avoid this in C and C++, I'm not sure about C, but in C++ certainly they have a notion of temporary extension or promotion. I forget what their terminology is, right? But the idea of being like, oh, this is often a foot gun. Let's just try and like make this live longer to prevent this. And Rust does the same thing. Obviously, Rust has a borrow checker, and all of the temporaries still get borrow checked. So it wasn't necessarily a huge priority as of Rust 1.0 to rigorously go through and determine in every single position what the exact temporary extension is. And so that's the first extended. There are two. There's extending automatic temporary lifetime extension. The latter extension is referring to extending the lifetimes. This extends the feature of extension by making it long. So it's very poorly written. I think it is.
Well, it's funny, right? Because it's one of those things that's like it's technically accurate, but it's confusing to read.
It is clever when it should just be clear. But I think they probably couldn't they couldn't help themselves. So the idea is right. So there's various places in Rust. I think Marabas has a really great blog post on temporaries in Rust. We should link to. I'll make you link to it in the release notes. You'll find it just on my
sure,
description.
I'll find a way.
But it really goes over why this matters and why sometimes you want to be able to affect or change or influence what the lifetime of temporary is, just for ergonomics and convenience. You can always extend a lifetime manually by pulling out into a let binding, and at that point, it will live until its last use. That is per the normal borrowing rules. But this is still kind of a thing that could use some work in Rust. I think the upcoming edition, because this is June 2024, there will be an edition sometime, which will make further changes to Rust's lifetime rules for the case of ifs. So branches, and to making if let more in line with if rather than being in line with match, because if and match have different lifetime temporary rules, it turns out, for rather good reasons. And then if let just happened because of some naive desugaring to match as opposed to matching if. I'm doing the same thing. I
was going to say, you're doing the exact same thing as the headline.
Anyway, as far as this specific feature, do you want to talk about what this new change does?
Yeah, sure. So the intent here is that we have this temporary lifetime extension where variables just are allowed to hang around longer than you might think if you look at them. And this extension that they've made to this feature is that, let's say you have an expression like let a equals, and then you have an if with an else branch, and in the true branch of the if, you return a reference to something that you constructed inside of the branch. So like let's imagine it's a slice to something, for instance. Like the true branch returns a slice to something that was allocated inside of the branch. And the else also returns a reference to something that was allocated inside of that branch. Previously, this would not be allowed because the borrow checker would complain that, and rightfully so, after you've exited the if, the value inside of that branch doesn't live anymore. It's been dropped. And so you're not allowed to have a reference to it anymore. And that is still true for the majority of cases. But there's one case specifically where they allow this lifetime extension. And that is if the last expression in the if branches is a reference to a temporary. So temporary here being like a thing that constructs a value, like vec : from iter, and you just immediately take a reference to it, then that value, that temporary, hasn't been assigned to a variable in any way. And like if you think about it, then logically, it arguably should be dropped inside of the if, right? Because it was declared inside of the if, but it gets its lifetime extended instead now. So if you say, reference to vec from iter in the true branch, and you do something similar in the else branch, both of those temporaries get their lifetime extended such that those references are actually valid. So if you say, let a equals and then the if and else, a will now be allowed to be a reference into the temporary that was allocated in each branch, and the temporary will sort of be kept around for as long as that returned reference needs to live for. So the reference is now stored in A. The same is also true for match. So if you say let A equals, and then you do a match, and inside each of the match arms, you return a reference to an immediate temporary. Like, this is another example of jargon, right? Immediate temporary, but like it's a reference to a value that's constructed right there where you take the reference. So these two cases will now both work, and previously they would not. And this is consistent with like previously you could write, let A equals, and then just open a block. So there's no if, there's no branching, just open a block. Inside of the block ends with reference to a temporary, then that would work just fine. It just wouldn't work if there was a sort of branching construct there. But now the branching construct will also work. And so this is a backwards compatible change, because previously this just wouldn't compile, and now some programs will compile that didn't compile previously. And it's sort of a nice place of now you can avoid having to do a little bit more of like workarounds you might need otherwise to write this kind of pattern, where you have like an if else, and you just want to return a reference to something you compute in each branch. But again, it only works in the specific case where you return a reference to like an immediate temporary, like something where the expression for it is right after the ampersand. It does not work for like arbitrary values that were created in the scope of the if or the else. So now hopefully the title makes sense, right? It's extending automatic temporary lifetime extension.
Yes. So next up, frame pointers enabled in standard library builds. And so a frame pointer, so rather low level concept here. Thinking about how functions are called, or how execution of a function occurs at the assembly level. There is a value called the frame pointer, or there could be, in theory, a value called the frame pointer, where it tells you where the base of this function stack lives. And in the past, it was, as an optimization, very common to just not have one of these, or to deliberately, when compiling your code, to omit the frame pointer as a way of freeing up a register, which is made more sense in on older hardware where registers were more scarce. In modern hardware, it might just be kind of a pain, because it makes it easier to debug, to know what function you're currently in, or what function this any given statement's currently in, right? Which you can also do through other ways, like dwarf debug info, but there are trade-offs there. So now this is frame pointers are enabled in the standard library builds, but reminder that the standard library comes as a precompiled binary with your Rust toolchain, unless you want to use the unstable feature to build your own stud, which you can definitely do. Yeah, I'm not sure what the behavior is for outside of that. I'm not sure if there's a way to what the default is.
Yeah, so I think by default, Rust will still omit frame pointers by default on like Linux and Windows, but not macOS or something. Like the default differs by platform, but I think it defaults to building binaries without frame pointers, but it now ships the standard library with frame pointers, because that's much harder to change in clients. And I think there's still some debate about whether whether frame pointers should be enabled by default in sort of downstream binaries as well, but at least they made the decision for the standard library. I think one thing that's worth pointing out here is like the reason why frame pointers are sort of an interesting topic is because you don't really need them, as Ben said, because if you have a compiler that compiles the program for you, then it knows how many things it push, or how much stuff it pushes to the stack, right? Because the compiler gets to just look at your function definition, see how many things it has on its stack, like how many stack variables does it have. And so when you call the function, it increments the stack by that much, and when the function returns, it decrements it by the same amount. So it doesn't actually need to store that value. It's just like knowledge when you compile. The problem is that if you have if you have something that analyzes your program as it runs, so it doesn't have access to the source code anymore, it doesn't really know which stack variables it is. All it sees when it looks at the stack is just like a bunch of bits. And so if it tries to figure out, if it tries to like walk the frames which correspond to the function stack that you're currently in, it doesn't really have a way to do that because it's just a bunch of bits. It doesn't know how many bytes are this function versus how many bytes are the stack for another function. And so it needs to get that information from somewhere else, like Dwarf, or get that information from like PDB files, something like. There are a couple of different ways they could get that info, but it does need to be supplied separately. And that information is usually enough, but not always. It can be a little complicated. So frame pointers are just like explicitly storing the value on the stack of where each stack frame starts and ends. But that obviously means you are maintaining an additional thing in memory that isn't really needed to run the program, but it does tend to make debugging a fair bit easier. It makes the debugger's life easier.
And that's it for the main featured language features. So now getting to stabilized APIs, there's a bunch of things here. I think I wanted to look at the unchecked add, unchecked mul, unchecked sub methods that are now on all the integer types, where previously, if imagine so in Rust, right? So whenever addition, you'd use the addition operator. What happens is what happens at the runtime is determined by compiler flags, right? So you either get the chance to make sure that it wraps, or you get the chance to make sure that it panics. And by default, in debug mode, it will always panic because it assumes it is an error. In release mode, it wraps because it's guaranteed to wrap because it is faster while still being safe. But if you know for certain that your addition cannot overflow, then both of these checks or both of these behaviors might be undesirable, right? Because even though it is quote unquote fast to wrap using typical CPU operation, it might be possible to totally omit the addition in some cases if the compiler can prove that it's totally pointless. Or by saying this is impossible, it is impossible to overflow here, you are giving the compiler more information that it can use to optimize, which as long as you're sure that you know what you're doing, then that's great. So these are naturally unsafe functions. And previously, the way that you would achieve this is to do a checked add, which would give you a option. Is that how that works?
Yeah, the checked add returns an option.
Yes, and then you would use the unwrap unchecked unsafe method on options to just get the sum value out, which would be undefined behavior if it was actually none. And so this is kind of just a shorthand way of doing that operation. So I think it's a good ad, a good addition.
Good ad. I like that. Oh, I know what to do. Yeah. Another thing I thought was interesting that was stabilized was the len function on raw slices. So this is things like star const square bracket t, or star mute square bracket t, or non-null square bracket t. Right. So these are raw pointers. So they might point to things that aren't valid, that aren't, say, aligned, or null pointers or whatever. But they still have a safe len method now. And the reason for this is because something like a raw slice, like a star const square bracket t, is really a wide pointer, right? And it holds two values, two U-sized values. One of them is a pointer to the data, which may or may not point to a valid slice, but the other is the length of the slice. This is the same thing as if you have just a normal slice reference. It is really a wide pointer where one of the fields of the wide pointer, so to speak, is the pointer to the real data, and one of them is the length. Just like in a dynamic dispatch pointer, like a reference din to some trait, that's also a wide pointer where one of them is to the data, the other is to the v table of the trait that is dynamically dispatched. And so the observation here is that if you have a raw slice, you can actually get its length without having to look at the potentially invalid data pointer at all. And so now those convenience methods have just been added to both of these, or to all of these. That there's now both a len method, and there's also an is empty, because obviously if you can check the length, you can also check whether it's empty, and those can all be safe, which is really nice.
I also wanted to highlight the new UTF-8 chunks method on strings. On string slices, that is, or on on byte slices. which allows you to sort of operate over, it's kind of like a way of converting byte data to string data, where in Rust strings need to be UTF-8 encoded. But if you're not entirely sure that what you have is strictly UTF-8, this kind of lets you, there's already a function called from lossy, right? UTF-8 from lossy or str from lossy, which allows you to take a random arbitrary byte slice and then make it into mostly what you expect with some replacement characters inserted in between in the case of invalid UTF-8. This gives you more control over that. And so it gives you an iterator where first it gives you all of the valid UTF-8 from the byte slice. And if it encounters invalid UTF-8, then you can get that out as well and then continue on processing the invalid or the valid UTF-8 until the end of the string. And so if you currently use the bstr crate, BSTR crate in Rust to work with byte strings that might be UTF-8, this could let you get rid of that crate entirely, or maybe not. But I mean, you should definitely worth looking into. I think getting rid of dependencies is usually a pretty useful thing, even if they are quality dependencies.
Yeah, I think this is something we've talked about on the podcast before, right? That Rust is this interesting property where the standard library is not necessarily very wide, right? It doesn't include an HTTP server or anything, but it tries to be very deep. That the types it does provide you with, it gives you like very low level control over them. And I think this is a good example, right? If you have a byte slice, chances are one of the things you might want to do with it, if you're writing, relatively high performance or detail oriented software, low level control software, is that you might actually want to decode partially valid UTF-8 data. And then this is a very reasonable thing for the standard library to include on byte slices. Actually, along the similar lines, the CStr type, which is the null terminated string reference type in Rust, it has now a method called count bytes, which will literally count the number of bytes in the string. Like it just counts the number of bytes until the null terminator. This is something you could obviously do yourself, but now there's a method for it. And crucially, it's distinct from len. If you called len on a CStr, you would get the number of characters. Like I think CStr still is UTF-8, although let me double check that I'm not lying here. Null terminated. Oh no, it's a null terminated array of bytes. Oh, there was no len on it before. That's the answer for that. There was no len method on this before, and part of this I think is because people have learned in Rust that like len means zero cost. Like len is fast on a slice because, as we talked about before, it's a wide pointer, so it just has the length right there. Whereas for CStr, you actually need to walk the whole byte string, which might be very long, in order to figure out how long that byte string was. And so now there's a method in the standard library for it. And my guess is one of the reasons it didn't land earlier was bike shedding around what it should be called, so that people don't assume that it's also fast. And I guess count bytes is what they landed on.
Yeah, my last API stabilized this release is the NonZero type, num::NonZero. So Rust currently has various, for all the integer types, so U8, I32, etc., there are non-zero variants of all of these, where the value of asserting that any given int contained in those types is non-zero is that it lets you benefit from the enum niche optimizations. For example, if you have an option of a U8 that is normally 2 bytes, because it has to put the tag somewhere to know what, or to know whether or not it is an option, a sum or a none, that needs to be stored somewhere. And then it's already using an entire byte to store the value of the U8. And so the non-zero types let you say, hey, we'll just say that this value can't ever be 0. And that lets the compiler use the 0 value to say, hey, if the value of this thing is 0, this byte is 0, we know it's none. Otherwise, it's sum of whatever the rest of the byte is. So now we have this generic non-zero struct. Instead of having to say non-zero U8 or non-zero I32, you can have non-zero and then have those primitives be a parameter to this struct. So that's kind of neat.
Do you have a sense of why we didn't have this before? Like why did we first get non-zero usize, non-zero U64, non-zero U8 as like separate types with no generics? And then now we have a generic version of it.
I'm not sure. So I do know that, so in order to work, this struct this type only works with things that have the zeroable primitive trait, which is a trait that Rust unstably implements for all of the integer types.
I
So
see.
I'm not
Okay.
sure, maybe that was something before that was being bike shedded.
Yeah, that sounds about right. I mean, I know there's been a bunch of debate about whether Rust should have sort of numeric traits,
Yeah.
right? To like, this thing is kind of like a number traits. And it's been like, there is like the num traits crate that provides some of this, but like whether some of that should actually be in the standard library. And I guess non-zero is a good example of something that it only makes sense for number types, but there's no meaningful way to say number types in Rust at the moment. And so at the very least, they needed to land on like, how do you define what is zero, which probably depended on things like having constants and traits, for instance, to define the zero value in a const setting.
And I think part of the reason, too, might have been that it might just not have gotten a lot of scrutiny, where it's understood that the non-zero types are kind of a temporary workaround for the inability to specify which values you want to be uninhabited. And so the idea is that in the long term, we should be able to, for any arbitrary bit pattern in our type, maybe not any arbitrary, but for types of patterns that aren't just zero, we should be able to say, hey, compiler, use this as a niche to store whatever the heck you want in there, which would allow the option optimization to occur, and you could make it be the max or the min, or it could be like, if you had a signed type, it could be the lowest, the bottom negative number, and that makes your range symmetric now. Ooh, isn't that pretty, right? So
yeah,
in theory, that should eventually subsume and deprecate all of these non-zero types. But I think that's called...
Yeah, and the extreme version of this, right, is something like refinement types, where you can say, this is a U8, but I know its value is always between 17 and 38. And so therefore, the compiler could know that all the other bit patterns are actually valid. And so like, you could have an option of this type and still have no extra overhead.
Yes, and I think...
and it gets infinitely complicated.
I think in Rust, rather than saying refinement type, people have called this pattern types. And I'm unclear what the status of the pattern types various proposals currently are. So anyway.
I think the last one, so there are two that could be called out, but I'm only going to call out one of them. So the one I'm not going to call out beyond the name is IO error downcast, because this is something that I suspect a small number of people have really wanted, and that's now stabilized. So if you're listening to this and you're like, oh man, I've been waiting for that forever, it's now stabilized. Congratulations. That's exciting for you. The other thing that I will cut out in a little bit more detail is path absolute. So the path module in standard library now has a method called absolute, which, as its name implies, it takes a relative path and it gives you back an absolute path. So effectively, it joins the current working directory with the relative path, if it is relative. And I think it also eliminates, if you have, for example, /a/b/dot/c, then it will return you like /a/c. I think it resolves dot dots. Although I would have to double check that. But crucially, it is different from canonicalize, which is a method that already existed in the path module. So canonicalize will also turn any path into an absolute path, but canonicalize will also resolve symlinks while doing so, whereas absolute will not do that. So it will not access your file system at all, essentially. It will only grab the current working directory from whatever it uses to access that, and then it does not access the file system. It just treats the path based on its path separators in order to construct the absolute path. And so this can be handy if, for instance, have a path to a file system you don't actually have access to, but you do know the path to where you are. You're just not allowed to access anything under there, but you still want to turn it into absolute. And so that's now in the standard library. And then, as always, I've done a dive into the detailed release notes. And there are a couple of things worth calling out here. One of them is that in 179, a bunch of additional WASM target features were stabilized. Specifically, one's is called here from target features from WASM phase 4 and 5. Now, I don't know what phase 4 and 5 are, really. There's a bunch of links to like deep WASM release documentation about this, but the features that were stabilized are things like import-export of mutable globals and bulk memory operations, which sounds exciting, but I haven't worked enough with WASM to say whether it's exciting, but I thought it was worth calling out that now, we keep seeing more and more parts of the evolving WebAssembly spec being supported in Rust, which is nice to see. Relax SIMD is not yet supported yet, sadly. It's on target for a future stabilization. There's also an MR that went into 179 that documents overrides of the clone from method on the clone trait in types from core and std. So a brief aside here on clone from. So the clone trait we normally just use for the clone method, but it also has a clone from method. And the idea is that imagine you have some existing value of a type, like you have some existing string, for instance, and you have that in a variable x. And now you want to make x hold the value of some other string y. Well, then you could say x equals y dot clone. But in doing so, you'd be throwing away the fact that x might already have an allocation. It might already have an allocation of a string that maybe is long enough to hold all the bytes of y. But when you write it that way, x equals y dot clone, you're going to essentially drop x and then allocate a new string and put that into x. Clone from allows you to work past this. So clone from lets you say x dot clone from reference to y. And that way it's generally like allocation preserving. It tries to avoid doing any work in the cloning that can be avoided because you already had an instance of the type from before. There's a clip lint, for example, that tells you cases where you might be able to use this to speed up your application, although it is mostly a performance concern. There's no correctness advantage. But the standard library does implements clone from, like specially for a bunch of types like strings or vectors, where there's like a meaningful way in which clone from can be more efficient than just doing the normal clone dance. And what happened in this PR is that any place where the clone from implementation is not just like a call clone from of all of the fields, like basically a derive clone from, but where it actually does some logic, such as in vector string, then now there's documentation added to the method that says specifically what that clone from implementation sort of guarantees, like what optimization it implements. So now you can go look at something like binary heap or a vec deck or a string or a vec. You can look at their clone from method and it will tell you the ways in which it is superior to clone when you're able to use it. So I thought that was a nice touch of like documenting the unusual implementations of a method. Another thing from the detailed release notes that I saw is that Cargo has now switched to using gitoxide by default for listing files. Gitoxide is a re-implementation of Git that is fully in Rust. So normally, whenever things need to integrate with Git, they tend to either invoke the command line tool or use this crate called libgit2, which is written in C. I don't think it's C++ even, I think it's C. Gitoxide is an effort to basically port that entire library to Rust and not have any C dependencies. And there's a bunch of ways in which that makes it faster and safer, although it's obviously a major undertaking. But Cargo now has a few parts of Cargo that use Gitoxide instead of Git2, with the hope to eventually drop the Git2 dependency entirely to avoid that C dependency in the Cargo project. And now they've moved the Cargo commands that will list files to now, like cargo package dash list, for example, to now use gitoxide instead. And it turns out one of the nice advantages of this is that that command has now gotten a lot faster because the gitoxide one is faster than the git2 one. And I thought that was like an interesting insight into the deeper parts of cargo development. And then I think that the last two that I have are both about lints. So in 179, there was a new lint stabilized called unnameable types. This is a sort of evolution of, there originally was a trait called lint called private in public, which had a bunch of problems with it because it conflated a bunch of different concepts around the idea of type privacy and visibility. And it's now been refined by RFC 2145 to have a more specific lint called unnameable types, which, as its name implies, it will lint on types that cannot be named because, for example, you can't get to their path, but are still used in your public API, right? So imagine that you have a crate, and in that crate, you have some type. And let's say you have functions, for example, that either return values of that type or accept values of that type, but that type cannot be named by callers. Like if you tried to render your Rust doc, there wouldn't be a link for it because it's not nameable. It's not in the public API, and yet it's used in the public API. This lint is allowed by default, and the reason for this is because there are some legitimate patterns where you want to be able to do this. such as sealed traits, but it can be very useful to turn on if you're not using any of those features, or to selectively turn it off, because it can highlight places where you genuinely forgot, right? Like imagine you have a public type that you intended to be public, but you put it inside of a mod and that mod is not marked as pub. Then that type, even though it says pub on the struct definition, isn't actually accessible to users. And it can be really easy to miss these problems. And so turning on like warning for the unnameable types lint is now going to highlight these for you. And then the last lint is new lint in Clippy called manual clamp, which tries to detect manual implementations of the clamp function. So the clamp function is input.clamp, and it takes 2 arguments, min and max, and it returns input, but min if input is less than min, and max if input is more than max. And so this Clippy lint will actually look for code that looks like if input is more than max, then max, else if input is less than min, then min, else input. It will look for the code that has that structure and say, hey, you should probably just use clamp here instead. And I think this is it's a good example of what Clippy is really good at, right? Identifying these patterns where there's a much simpler and more efficient construct, and it can just tell you, hey, just replace the code exactly the code you had with exactly this, and then you pass -- fix and your code is better now. And it makes me love Clippy even more. I think that's all I had for 179. Did you have anything else to add here, Ben?
Nope, I'm all good. Let's proceed.
Amazing. So now we're gonna admit that actually we lied when we said that it was June 14th, because it is actually July 26th. It is the day after Rust 180 came out.
I bet we had you fooled, huh?
Yeah, we're really good liars, Ben. Rust 180 is a very round number, which makes me happy. And there's a bunch of cool stuff that landed here. Do you want to kick us off with LazyCell and LazyLock?
Sure. I feel like in the past we talked about LazyCell and LazyLock before. Some context, I think when once cell and once lock were stabilized, probably we did this. And so I won't belabor the point too much. But they're really cool. If you are a user of the LazyStatic or once cell crates, this is another example of now you can jettison those entirely, probably, unless you're doing something very specific. Specifically, the LazyLock type is a good replacement for the LazyStatic macro if you're using that crate. And if you're already using the one cell crate, you're probably already using the lazy type from that crate, which is equivalent to LazyLock in standard library. It was delayed for a long time because of naming, right? So the one cell library, the crate, provides both synchronous and non-synchronous. I can't say asynchronous. It means something entirely different.
You gotta be careful with your words.
Sync and non-sync versions of this sort of lazy initialization primitive. And normally it's kind of again, now there is, for completeness, right? Rust wants to be a deep, if not necessarily wide, standard library. And so it wants to accommodate all these use cases, even if they're fairly niche, as long as it can do it, in a reasonably consistent and satisfying way. And so even though there are versions of these that are not sync, so there are standard cell, lazy cell, and once cell are versions of these types that cannot be used in statics because statics are required to be sync in Rust. Instead, you would want to use the standard sync, once lock, or LazyLock types, and usually you probably just want LazyLock. And so of these 4 types, just ignore the rest, use standard sync LazyLock, and it lets you have lazily initialized static variables. It's funny because when these types were first conceived, Rust had very little const machinery for constant evaluation or compile time evaluation. And so the reason you needed to have a LazyStatic crate and macro as of Rust 1.0 is that Rust 1.0 had barely anything aside from basic integer literals that were allowed in const expressions. Nowadays, the need for this crate is much less because the const FN is getting more and more powerful with every release, but sometimes you still want to do something like, for example, allocate a hash map, which can be rather tricky to do at compile time if you want to access that data at runtime. And so LazyLock is still great for that because it lets you give it an initialization closure, which it will run automatically for you on the first access. And it guarantees it only runs once and across, no matter how many threads you're using or how many people are accessing it. So it's all re-entrant. It's all totally safe. It's really great. Almost no overhead. So I highly recommend using this.
Yeah, I think the trick they pulled here is interesting too, right? Like when you declare a static, the value you give that static must be const. Like it's a const expression effectively. But the trick they pulled to allow you to have a non-const function like constructing a hash map or getting the current time is that the the expression you give for initializing the static is like LazyLock : new, and then you pass it a function pointer basically. So at compile time, the only thing that really happens is that you store, I guess, the function pointer. I'm not entirely sure how that works. I think it's just the function pointer. And then at runtime, that function pointer will get called in order to construct the value. Like the first time the LazyLock is accessed.
The first time. There's still needs to allocate space for the eventual type as well. That's going to be in there. It just works. I really wouldn't worry about it too much. It just works.
And I guess it's worth just making it explicit that the difference between LazyLock and onceLock is that with LazyLock, you can declare how to construct the value when you declare the static. Whereas for onceLock, you have to do it when you first access the thing, or every time you access the thing potentially.
I would do the other way around, where I would qualify it as LazyLock is more restrictive because there's only one place that you can ever actually make the initialization. And so if you wanted to have a varied initialization or have things initialized in different ways depending on where it gets initialized from, onceLock is more flexible in that way, but also potentially not useful and more repetitive.
I guess the other argument for onceLock is that onceLock, your initializer can be a closure, whereas that's not the case for LazyLock. Right. So for onceLock, where you initialize the value, you might have access to like stack variables or something. Like you actually have, like the program has been running for a while, potentially computing a bunch of things, and you can take that into account when constructing the value that you store in the onceLock. Whereas for LazyLock, the value that you instantiate has to be like effectively a static, right? It doesn't get to look at any current execution context.
Keeping in mind that you can use LazyLocks in non-static contexts, you could pass it a closure if you were within a function body, for example. The thing is, if you wanted to have a static and you wanted to capture from variables or values the closure in a function, you couldn't use LazyLock. You'd have to use onceLock.
Right. I guess the other thing that you did say in general, just use LazyLock, and I think it may be useful to mention where would you use LazyCell? Like when is it ever useful? The thing that's like not send and sync or not sync.
I don't know. Right. So like even in the original, it was some question of like, are these types useful enough to even have in stud? And like there were some arguments in the original tracking issue for why they're actually useful. I think if you go to the onceCell crate documentation, it makes an argument for why the non-sync versions what they could be used for.
Yeah, I think the blog post outlines that you could use them in thread local, right? I think is the best one, where because it's thread local, it doesn't need to be accessed from other threads, and so therefore it's fine for it not to be sync. So you could use it, although there's a question of like how much performance does that really buy you?
Yeah, it may just be like how Rust has both RC and ARC, where one is allowed to be exist in sync and one is not. And the only real difference is that RC, the non-sync version, has a slight performance benefit from not needing to do atomic operations. That may just be like if you really have it might be one to avoid the case where people have an extreme performance need but also want to use this, but they couldn't because they don't want to have the overhead of checking a single atomic variable every time on every access.
That's probably right.
So I think it's atomic Boolean even.
The other thing I like about the story of LazyCell and LazyLock is how this is a great example of Rust's general preference for like testing things out in the ecosystem, right? Like you had the lazy static crate first and then the onceCell crate, and they had extreme adoption, right? Like they were used in so many crates, both, both random like binaries and stuff, but also in crates that were then used very widely. And so they sort of proved themselves as clearly this is a thing that like the majority of Rust programs actually need. And so that became a big part of the motivation for bringing it into the standard library. But they wouldn't have brought it into the standard library from day one. It's the fact that it was proven in the ecosystem, both the API, but also the implementation, that allowed it to mature over time to the point where now what lands is actually like a thing we're willing to commit to long term. All right, so next on the list for 180 is checked config names and values. This is a new feature of Cargo, where now when you build Rust projects, or rather it's a feature of Rust C that landed in 179, but it's a feature of Cargo in 180 to enable that feature in Rust C, which is that any time that you use like the config conditional compilation attribute on your Rust code, Rust will now check that the value inside of the config is actually reasonable. So for example, if you put in there feature, the example from the blog post is like feature equals crayon, when your feature was actually named rayon, not crayon, then Rust will now tell you, hey, you have a conditional compilation attribute here, but you're naming a feature that your crate doesn't have. Are you sure you didn't mean this other value? This is obviously good, right? It will catch places where you just like mistyped your config, but it's not just for features. There are some crates like Loom, for instance, that it recommends that people set custom configs, which is like passing the --config option to Rust C, so that you can say, pound config open bracket Loom without saying feature equal. It's like a config flag. You also see this for more standard crates that just always enable it, like Clippy, Rust format. You also see it for other things that are built into the language, like target OS equals, like allow attributes. Well, allow isn't a config, but config doc, for instance, right? So there are a bunch of these config things that are valid but are not features, and now all of those will be checked for you. And so what's built into Cargo is basically a list of the things that are always available and the features from your crate. But if you have additional things that you enable as configs, such as Loom, you do have to tell Cargo about those now. Otherwise, when you build, you're going to get a bunch of warnings that say, hey, you have code here that says config Loom, but Loom is not a well-defined config parameter. And so in Cargo TOML, there's now a new lints table, and the lints table itself is not new, but there's a new entry in the lints table that is unexpected_configs. And there you can say the following config values are actually okay. There's an example in the blog post that tells you exactly the syntax, but you can, for example, there say that the config flag Loom is valid, or the config flag, foo is valid when given the values bar or baz. So that way, if you use, say, config foo equals umbrella, then it would fail, saying the only valid values for foo are bar and baz. And so it gives you pretty nice control here over what are the valid things to put in config. And if you don't use one of those, if you don't use something that it recognizes, it will call you out for saying, this is probably not what you meant to do. Or if it is, adjust your config. No pun intended. The other thing that landed in 180 that's pretty nice is a simple enough feature in a way, is support for exclusive ranges and patterns. So previously in Rust, you were able to say like match on a number or a string or a character, and you could, in the match, have match arms like from the character literal A to character literal Z, like dot dot equals tick A tick dot dot equals tick Z tick, do this. And from 0 to 9, do this. And Rust would tell you if you ever had missing ranges in there. So if you didn't cover, let's say you were matching on numbers, so let's say you were matching on a U8, it would check that you cover all of the possible numbers or values of a U8 between the different ranges that you list in your arms. However, a condition of this was that you could only use inclusive ranges or open ranges. So you could only use like A dot dot equals B or dot dot equals B, so everything up to and including B, or anything from A and onward. So either the start had to be inclusive or left out, and the end had to be inclusive or left out. But this can be kind of awkward sometimes, where you want to be able to say things like any value that's smaller than, say, 10. For numbers, it's easy to convert between an inclusive and an exclusive range, but it's not true for something like floats. Although I don't know if floats are supported here yet, but for a float, you can imagine you want to say, do this for numbers that are less than 1. But you can't make that dot dot equals like 0.9999999 because there's no value you could give there. Like you could always add another 9. And so converting between these ranges isn't trivial. But what's now landed in Rust 180 is that the ranges you can give for match arms can now use exclusive ranges as well. So you can say things like dot dot 1.0, do this, and then 1.0 dot dot whatever, do this, meaning the first arm of that will exclude the value 1.0, which was previously pretty annoying. Okay, Ben, so now that we've passed that, we're down to the list of stabilized APIs. Do anything here strike you as particularly interesting?
Yeah, I think there's a lot of really good new APIs in this release. And so I want to call out the flattened methods on vec and slices. And so there's vec into flattened and slice as flattened. And so vec into flattened, if you have a two-dimensional vector, you can make it one-dimensional. And so essentially you have a vector of slices. Imagine a vector that is 5 long, and then there are, each element is a slice of 10 elements. You can make that into one vector of 50 elements.
I think it's specifically arrays, right?
I think it's a slice. I think it works on any slice. I think it's an unsized. Oh, you're right. No, it is fixed size.
Yeah, because if it were a slice, it wouldn't be owned, right? So I think that's probably why. It needs to be an array so that you can take ownership of the values and make them into the vec.
Yes. And then same thing for the slice version, where it is a slice of arrays. If you have a slice of arrays of length n, and then you can make it into a one-dimensional flattened version of that slice, which is very nice, very convenient to use.
And I think the thing that's really nice about as flattened is that it's free.
Yes.
Right? Like it takes a slice of arrays and it returns you a reference to a slice of T. So like there's no allocation. It's not an iterator. It just happens to be that the memory layout of a slice of arrays is the same as just a flat slice.
Yeah, so if you happen to be transmuting arrays around in any way to try and get around this, you no longer need to. This is a safe API you can just rely on. I also wanted to call out, again, on slices, there is a new trim ASCII feature. I'm calling it out because in our workplace, we had to have a tiny little helper function we got rid of everywhere because we no longer needed this, where it just lets you say, hey, normally on strings, there's a trim method. But what if you don't have a string? What if you have a byte slice that is ASCII or may not be ASCII, or just a byte slice where you want to get rid of all the white space in there? I think we were doing this too in processing certificates of X509 or something like that, where they are byte slices, but we don't want to convert them to strings or ASCII. We want to leave them as they are, but we want to get rid of the white space. And so this just says, hey, you have your slice, call trim ASCII, and any leading or trailing characters or bytes that match the ASCII whitespace, as determined by the existing method U8 is ASCII whitespace, will just be eliminated. And you'll get a reference to the subslice, the slice of that array that does not have those characters in it. And there's also trim ASCII start and trim ASCII end on those as well, because you only want to get rid of whitespace from the front or the back. And these also exist on the str type as well. So in case you just want to get rid of specifically ASCII whitespace and not non-ASCII whitespace. If you have a str, you already have a UTF-8 thing, but Unicode includes many things that are whitespace conceivably that would be trimmed by trim. And if you just want to get rid of the whitespace, that is, I guess that's just space, right? Or I guess it gets to be space, horizontal tab, line feed, form feed, and carriage return. Those are all the ASCII whitespaces, according to the documentation of is ASCII whitespace. And so, yeah, I think those are just again, neat little things of, not wide, but deep standard library of trying to make it convenient for all the types that do exist.
I also noticed in the stabilized APIs, there's like a bunch of methods that have been added to non-null. And I think these are methods that already existed on raw pointers, but they have been added to non-null as well.
And what is non-null?
So non-null is a type that represents a pointer that is not null.
So it's like a non-zero type.
It's basically a non-zero version of the raw pointer type. But do you know why? Because I think non-null already implements asref to pointer or something. So I feel like you already had these methods.
The fact that there's so many stabilized in this release, I assume if we go to the tracking issue, we'll see the argument there.
Yeah, I couldn't immediately find it.
It's called, so the feature is non-null convenience.
Non-null convenience. Oh, actually, I think this is actually the reason, is that it doesn't implement deref or asref to pointer, because that would give you a reference to a raw pointer, which isn't really the thing that you want. Realistically, what you really want is you want all of these methods that are on pointers from non-null, but they don't really have a way to forward them. And so they had to be added as explicit functions on non-null, and that's what landed here. Because otherwise you would, non-null has a method that is .as pointer, which gives you back the raw pointer. But this way you don't have to call, if you wanted to say do, I don't know, a read from a non-null, previously you would have to take the non-null .as pointer .read. And now you can just non-null read directly.
All right. And then the last API I wanted to call out is the impl of iterator for boxed slices. And so normally in Rust, if you have a vector, for example, it is a heap allocated array, quote unquote, right? Where it is, but it's also a growable array, crucially. And so a vec does not have a fixed size. It has a size that can vary over time, whereas a boxed slice does not. And so if you have the usual box thing for putting things on the heap, and you give it a slice, at that point, the slice size is fixed. There's no longer any way to increase the size of it. And so sometimes people find this useful as compared to a vec. Now, this boxed slice implements into iterator by default. Previously, you would need to go through and convert the box to a vec, the box slice to a vec, and then iterate over it. Now you can just call into iter directly on it or use it directly in the for loop syntax to iterate over it, which is very convenient.
I remember something about this causing like a breakage of some kind with the time crate. Is that right?
I'm not sure. I did hear something about that, maybe. I think...
Yeah, I think there was something where the time crate was relying on... They called into iter on something that was boxed, and they were just using like box underscore. And so they were relying on the compiler inferring what the underscore type was.
Okay.
And previously that was fine because there was only one implementation of into iterator for box of t, and that would be if the t is into iterator. But now this explicit additional implementation made that call ambiguous in the time crate. And so they had to like make a change to the time crate and then roll that out. And then I think that this got delayed. It was supposed to be stabilized earlier. It's like an interesting exercise in just how subtle it can be to design a standard library.
Yeah, Rust is usually pretty good about checking and making sure that there's no known breakage in the public Rust.io database, but sometimes I guess things slip through.
Yeah, I think there was specifically like an older version of time that had the problem. So you wouldn't catch it on the newest versions, but you would catch it on older ones.
Yeah, so normally Crater only runs on the newest version,
right?
I think, of things. So, okay, yeah.
So for me, under stabilized APIs, there are a couple of things that stick out here as well. One of them that I thought was kind of nice is on option, there's now a method called takeIf. So option as a method, and it has had for a long time, called take, which if you have an option that is sum, it will make the option be none, and it will return you the owned value that was previously in the sum. So it takes an option and returns an option and leaves the option itself as none at the end, regardless of what its previous value was. And the return value is sum if the previous value was sum and none otherwise. Takeif is the same kind of thing, except that you pass in a function that returns a Boolean, and it will only take the value out of the sum if something is true about it. So crucially, this means that it's a little bit nicer now to have an expression where you want to say, if the value is sum and its value is, let's say, less than 42, then take it out. Otherwise, leave it as is. Previously, you would have to like match on if it was sum, and if it was sum, then check its value for 42, and then store that somewhere, and then after the if, then do take, but only if the Boolean was true. So it was actually kind of annoying. Whereas now you can just do, x.takeIf, and then you pass a closure with an argument v that represents the value inside of a sum if it is sum, and you just provide a conditional expression in there that returns true or false depending on whether you want to take the value. So it's like a quality of life improvement for using options in this sort of dynamic way for whether you want to take them. The other thing that I've seen that was stabilized that I thought maybe is worth calling out is that we now have an implementation of 2 bits and from bits from IPv4 or an IPv6 addresses. So the thinking here is that an IPv4 address is really 4 bytes, right? It's 4 U8s, and we often explain them this way, right? Like my IP address is 10.0.0.1 or something. But realistically, when you send this over the wire, what you actually send over the wire is a U32, or it's often considered a 4-byte field. Like an IPv4 address is really just one number. It's one U32. Similarly, an IPv6 address is one U64. Am I lying? Sorry, one U128. I am lying. And so now in the standard library, there is a function that will just take, let's say, an IPv4, and it will give you back a U32. Like it'll give you back the U32 encoding of that IPv4 address, rather than giving you the constituent component bytes, which is often how humans think about it, but often not how machines think about it. So this is another example of like, this is a common use of IP addresses that is now enabled by the standard library.
But now, Ben, the time has come.
I'm finally going to kick you out. Now it's going to be my show. You
No!
don't get to be here anymore.
No, Jon, what are you doing?
Yeah, I'm going to kick you away. Leave, Ben. Never come back. Never show your face here again. Except the next time.
Play me out.
And with that, I suppose you are stuck with me for the rest of the episode, but I'll still try to keep it interesting. As usual, I've done my own little deep dive into the detailed release notes, and as always, there are a couple of things that stood out to me as being interesting. One of them is that a new target at Tier 3 has been added to Rust, called x86-64 Unknown Linux None. Now, this is different from x86-64 Unknown None, which has been added in the past, which is just like, I'm on x64, but I don't have any OS under me. Like, it's just unknown none, it's bare metal. Whereas this is x86-64 unknown Linux none. So it's still a Linux binary, still like an ELF binary that accesses the Linux kernel, for example. But the last none there is as opposed to, for example, GCC. So what this is explicitly saying is this is a target that targets Linux machines, but it does not link with libc. So the intent here, the reason this landed, was basically for people who want to write binaries that either do not pull in libc at all, so that they're, for example, more portable or can run on non-GNU environments, but also so that people can write libc implementations themselves in Rust. Because then obviously you don't want to link to a different one because you're writing your own. And so now you can target this, and the resulting, shared object file or binary that you produce will not have a dependency on libc. And so it can be something like a libc itself. There used to be, or there are still, ways in which you can kind of do this yourself with the existing targets. Like you'd use, x86-64 unknown Linux GNU, and then use like no stud plus some other bits to make this work. But this just makes it hack free. And I think it's a nice addition. Obviously, right now, it does not have alloc support or stud support because those both ultimately come from the fact that you link with libc. So this then doesn't provide those, although you could use something like Rustix to add that back in if you really needed to. Another thing that was interesting in 180 is that the size of and align of functions from stdmem and size of val and align of val were added to the prelude. So these functions you no longer need to call or import through stdmem. You can now just use size of and align of directly in any of your Rust code, and it will just work. The interesting thing here is that this didn't require an addition boundary to add this to the prelude. And the reason for that is because the prelude never takes precedence over other imports in a file. So if someone else already had a file where they either explicitly imported a size of some kind, or if they wrote their own function called size of, those would take preference over what was sort of in the implicit prelude of Rust. And so as a result, no code that previously compiled would now end up using the wrong size of, for example. It is just a quality of life improvement. And the argument for adding them there is like, these are pretty widely used and they're also unambiguous, right? When you write size of, in general, people will know what you refer to. It's not like something like CMP, like stud compare, or clamp, maybe like stud compare clamp or stud compare max, where like those feel a little weird to add to the prelude because there could be multiple different methods that meaningfully had that function, that name, whereas size of is pretty unambiguously referred to as what is the size of a value or a type. The other thing that landed in 180 is a warn by default lint called never type fallback flowing into unsafe. That's a mouthful. I'll link in the show notes for a description of this lint. But what's really interesting about this lint is basically the observation that in Rust, they want to add this thing called the never type. And this has been debated for a long time. The never type is the just exclamation mark. And you can already use it in some places. If you have a function that never returns, or that, like, for example, it goes into an infinite loop, then you can have a function foo, and you can write arrow and then exclamation mark to say never. It never returns. And this is something that they want to start using in more places. Or rather, they want it to become a type that can be inferred by the compiler as well. Currently, there's like an interesting case where the compiler will sometimes, when it has what's an example of this? Let's say you had a function main and you say, let x equals loop. That's the entire program. What is the type of x? So previously in Rust, what would happen is that the compiler would look at loop and go, okay, the value of this expression is the never type because it never returns. And then it tries to figure out what is the type of X. Well, X doesn't have a type, and so we need to assign it a type. But Rust wouldn't necessarily assign it the type of never, because then it becomes really hard to process anything that comes below for various complicated reasons. But what Rust would normally do instead is it would actually say, let me just treat X as though its type is the unit type, like just empty parentheses, and then just continue compiling the program following there. And then, obviously it would highlight this code is not reachable and whatnot, but it still has to pick a type for the purposes of type inference. And previously that type, that fallback type, as it's called, would often be unit. What they want to move to is for the fallback type to continue to be never, to basically not really have a fallback type in that sense. They want the fallback type to not be unit. And whether it's the never type or some other type is not terribly important, but like they want it to not be unit anymore because unit has other meanings. What they realize, though, is that this current behavior of the fallback type being unit has some interesting implications where you might have unsafe code that is safe only when the fallback type is unit, but not safe if it is some other type. An example of this would be something like if you have an if expression where you have, if true, then return. So return has a type of never, else unsafe stud mem zeroed. So stud mem zeroed is generic over some type t, and it will generate a type of that t by just zeroing out memory. The problem here is that stud mem zeroed, the compiler has to infer what the generic type t is for zeroed. And it tries to do that by making it match what the type of the overall if expression is. But the overall type of the if expression is never, because the true branch has return and the else branch is ambiguous and is trying to figure out what type to use. So it would use the fallback type. What that means is in previous versions of Rust and still, that zeroed would generate a unit type, which is totally fine. It's totally fine to generate using zeroed the unit type because the empty bit pattern is valid for it. However, if they change the fallback type to not be unit or to make it just explicitly be the never type, then this unsafe call to mem zeroed would no longer be okay, because now zeroed would generate an instance of the never type by just generating zeroed bits. But the problem is the never type is never supposed to have an instantiation, and so this would just completely break. What they're worried about is that there's a bunch of unsafe code that might have been written that relies on the fallback type being unit. And so as a result, they can't change the fallback type because that such unsafe code might eventually be broken. And so they introduce this lint. That's the long story short, that they introduce this lint in order to highlight places where the fallback type gets resolved into unsafe blocks, to highlight that this unsafe code really needs to change. It needs to disambiguate what type it's constructing so that in the future, if we change the fallback type, the code remains safe. So this feels like, I don't know if this is something that will change at an addition boundary or whether this is something that eventually they'll just make a hard lint, like a sort of future compatibility lint. But this is like highlighting this is a place where your unsafe code might actually do the wrong thing. And I think we're almost at the end. The other thing that comes to mind that is that there were two interesting places where the standard library will now panic where previously it would not. And it's sad that I kicked Ben out because this would be a good question to ask Ben. Rust has to decide on a sort of policy for when is it okay for the standard library to panic? And when is it okay for the standard library to not just panic, but to like fully abort the process? And there are two things that were added in 180. One of them is so in the standard library, there's now an owned FD type, so owned file descriptor type, that just holds a Linux file descriptor, but it believes that it owns that file descriptor. So when that file descriptor, that owned file descriptor is dropped, it will call close, like it will close the thing with the operating system. If the implementation of drop for that type detects that the file descriptor has already been closed elsewhere, or it's not just implementation of drop, it's like if anywhere in the use of owned FD detects that the file descriptor has already been closed, that means that the file descriptor wasn't owned in the first place, right? Because someone else was able to close it. And so this indicates that something is like really, really wrong. You thought you owned this file descriptor, but you did not. this will now trigger a process abort in Rust in the standard library if it ever sort of trips this check. And I think it's a really interesting case of the standard library enforcing a safety check by panic, or in this case, going all the way to aborting, because they've sort of concluded this is so bad, like things are so severely broken if this has ever occurred, that we're gonna cut our losses and say it's better to terminate the program and make that decision on behalf of the caller, right? Because there's no real way for the caller to have this not happen, especially with a process abort. The other case of this is the standard library will now panic if you, so on paths, so std path, there's a method called set extension that adds or sets the extension of a file path. And now it will panic if the argument provided to set extension adds a path separator, so like adds a slash, because that would make the path invalid and make it potentially just refer to a completely different file, which is something that clearly was not what you intended, and could potentially even become a security issue. And so the standard library has sort of unilaterally taken the decision that we will panic if this ever happens in order to safeguard essentially calling applications. And to be clear, I don't think these are necessarily the wrong decision. It's just an interesting topic of like, where does the boundary go for what is where it's right for the standard library to impose these kinds of checks on calling programs, as opposed to just allowing it to go through because that's what the program asked it to do. And the last, actually, there are a couple of more things I want to talk about. I thought I was near the end, but then I discovered I had more tabs open. So there is there's a change to Rustdoc so that if you have a type alias that is a type alias to an enum in another crate, previously that the rendering of your type alias would not list the variants of that enum, whereas now it will. So this is a very nice like quality of life improvement. Like it's an obvious improvement that you should show the variants when you have an alias to a sort of foreign enum, and now it does that. So that's a really nice improvement that I wanted to make sure to highlight. The next one is a change to Clippy, to specifically to the assigning clones lint. So we talked earlier about the idea of the clone from method on the clone trait. Well, previously there was a Clippy lint that would tell you, hey, you probably meant to use clone from here, or rather you could use clone from here, so why not do it? This used to be a warn by default lint. It has now been moved into the pedantic group, so it's now allow by default. And the rationale behind this move is that we want Clippy lints, the ones that are on by default, to always be important. So because otherwise you get like hundreds of warnings, and at that point you get sort of fatigue and you decide to not address them. And assigning clones is like, it's a slight performance improvement, but that's kind of all. And it makes the code arguably less readable. So we're just going to have it not be on by default. People can always still enable it, but this one doesn't feel worth the potential noise. And so I thought that was an interesting thing to call out, given we just talked about it a little bit. We also saw a couple of lints turn into hard errors in this release. These are things that like are they've been in the list of things that should like are future incompatibility lints, like lints that are known to eventually be planned for becoming hard errors. Like one of them is indirect structural match, which has been like in this state of it will soon become a hard error for years now. And I just thought is worth calling out that we do actually in Rust sometimes make lints move into hard errors when we say we're going to do that. And then the last two I wanted to call out are actually backwards incompatible changes that are sort of intentional on the part of the standard library. One of them is that for the 2024 edition, the setvar and envvar functions are going to be made unsafe. And there's a whole discussion about that we'll probably touch on when we talk about in a later episode about the 2024 edition. But crucially, this had an impact on Rust as of the 2018 edition when they introduced this feature in 2014. For the 2024 edition. Specifically, if you use the std env setvar and remove var functions in the 2018 edition, where they are still safe, they no longer implement the fn trait. and they can no longer be converted to safe function pointers. And this is because they really are unsafe. They've been changed, like the deep, true implementation of them has been changed to be unsafe. And so now they don't implement any of the like safe coercions to function pointers or to implementers of the FN trait. And this is backwards incompatible, right? It means that previously, if you passed std env setvar as like a function pointer argument to something else, then that code will start compiling now because it isn't a function pointer anymore. There's a workaround and everything, but this was considered acceptable breaking change because it's a safety fix to make it unsafe in 2024. And so if that has some implications for 2018, as long as they are relatively contained, that was deemed acceptable. And the other backwards incompatibility I want to highlight is that there were some changes to the implementation of locks. Here, there's some like soundness fixes for specifically the re-entrant lock guard, that it is no longer sync if the underlying type isn't sync. Previously, if you had a re-entrant lock guard, it would be sync regardless of whether the inner type was sync, which is just unsound. And so that was fixed in 180, but the impact this had is that the stood out lock and the stood error lock both use this type internally, which means that they are no longer sync either. So in Rust 180, stood out lock and stood error lock are no longer sync. And this was just deemed as being something that was sort of I think it was an unintentional regression. But when the regression was pointed out, I think the team sort of landed on, the underlying thing is an unsoundness fix, and the fix to reintroduce sync to stood out lock and stood error lock would be to add a mutex inside of it. That's the only way to make it safe. And that seems excessive. Like, we don't really want to do that. And so we would rather just say that these are not sync anymore and accept the resulting breakage. So it's marked as a soundness fix in the release notes. Okay, I think that's the end of Rust 180. So the last bit before we close here is going to be that there was a Rust 1.80.1 point release. This one is a relatively small one. It's basically a miscompilation when it comes to floats. So specifically, there are now some optimizations that are implemented specifically inside of Rust C, so not done by LLVM. And one of those turned out that it broke when comparing floats. That one was fixed in 80.1. And the other was a false positive in the dead code lint that meant that people get a bunch of false positives from the lint, which is really annoying. And so that was fixed as well. And with that, I think we're fully caught up now to as of August 9th, where we now obviously are. We were lying to you previously when we said we were at when did we even say we were? When we claimed that we're July 26th, but we're actually August 9th, and that's the real truth, is that we're right after Rust 180.1 was released. And so now I'll let the intro play us out, maybe. Let's do something like that, because I don't have Ben here to rant me out. Okay, Ben, I have a crazy idea. Mm-hmm. What if the next time we do this, we do another live stream?
I think that might be an interesting concept.
Stay tuned, folks, and you might hear from us that there'll be another one with our faces in it, where we talk live to you through a screen.
All right, see you around.
See you around.
Can I make a headache for the editor here? I need to go in 10 minutes. If I leave, will it mess everything up, or is it?
No, you should be all fine.